Number 10. The impossible flame. Picture an astronaut floating inside the International Space Station striking a match in the name of science. You expect the flame to flicker and die within seconds. In microgravity, there is no up or down. Hot air cannot rise. Convection, the invisible force that shapes every flame you have ever seen on Earth, simply does not exist. The flame should suffocate in its own combustion products almost immediately. That is what the physics textbooks predict. That is what NASA's combustion models guaranteed would happen. But here is the nightmare. The flame refuses to die. Instead of extinguishing, it transforms into a perfect blue sphere. It burns steadily for minutes, hovering in the darkness like a miniature alien sun. On Earth, flames are teardrop-shaped because hot gases rise and pull fresh oxygen downward in a continuous cycle. Remove gravity and that cycle breaks. The flame should consume all nearby oxygen within seconds and snuff itself out. Yet the spherical flames aboard the International Space Station during the flame extinguishment experiments, conducted by NASA's Glenn Research Center, did something impossible. They created their own oxygen flow through pure radiative heat transfer, a mechanism that was theoretically insignificant in every combustion model we had. The flames were not just surviving, they were rewriting the rules. Think about what this means. Humanity has been burning things for over 100,000 years. We have built internal combustion engines, jet turbines, and rocket motors. We have sent people to the moon on controlled explosions. Yet we fundamentally misunderstood how fire actually works. Our models were incomplete. Decades later, we still do not have equations that fully predict what a flame will do in microgravity. If we got fire wrong, what else have we gotten wrong? Number 9. The backwards bacteria. Take a petri dish filled with ordinary E. coli bacteria, seal it inside a container. Send it to the International Space Station for a routine microbiology study. You expect the bacteria to struggle. Microgravity is a stressor. Organisms under stress typically slow their growth, conserve energy, hunker down. That is basic biology. That is what every textbook on cellular stress response predicts. But here's what actually happened. The bacteria exploded. In space, E. coli grows 13 times faster than it does on Earth. 13 times. It does not just grow faster, it grows differently. The colonies form three-dimensional columnar structures that have never been observed in any laboratory on the planet. They stack upward in impossible towers, as if microgravity taught them architecture. Worse, they become more dangerous. Experiments conducted by Cheryl Mickerson at Arizona State University on space shuttle missions STS-115 and Paras. Salmonella bacteria in space showed a 73% increase in virulence. They became more resistant to antibiotics. They became better at invading human cells. Genetic analysis revealed that genes which should remain dormant were switching on. Genes that control stress response, biofilm formation, and pathogenicity were activating without any evolutionary pressure. This is not adaptation over generations. This is happening in days. The bacteria are not evolving. They are transforming. Right now, microbes aboard the International Space Station are learning to weaponize microgravity. We can engineer vaccines and antibiotics on Earth, but we cannot predict what bacteria will do when we remove gravity from the equation. Think about what this means for a Mars mission. 3 years in space, closed environment, recycled air and water. If an astronaut gets sick halfway to Mars, the pathogen they are fighting might be something we have never seen before, something our antibiotics were never designed to kill. Number 8. The quantum entanglement delay. In 2016, China launched the MISHIS satellite to perform the most precise test of quantum entanglement ever attempted in space. Quantum entanglement is Einstein's nightmare, the phenomenon he called spooky action at a distance. When two particles become entangled, measuring one instantly affects the other, no matter how far apart they are. Instantaneous means instantaneous, no delay, no travel time, no signal crossing the void. That is the iron law of quantum mechanics proven in thousands of ground-based experiments over decades. But here is the nightmare. The MISHIS satellite found a delay. A measurable, repeatable, impossible delay of 7 microseconds between the measurement of one photon and the correlation appearing in its entangled partner. 7 microseconds does not sound like much, but in quantum mechanics, instantaneous does not mean very fast. It means no time passes at all. The correlation should appear simultaneously as if distance does not exist. Yet space-based measurements conducted by Pan Jianwei and his team at the Chinese Academy of Sciences detected a gap, a lag, a violation of quantum non-locality that should not be possible. The delay is lurking in the void between entangled particles, hiding in plain sight. Ground-based experiments never saw this. The delay only appears when you perform the experiment in the vacuum of space, away from Earth's atmosphere and magnetic field. This suggests something terrifying. Either quantum mechanics is incomplete, missing a hidden variable or unknown medium that affects entangled states, or space itself has a structure we cannot detect, a fabric that slows quantum information in ways our equations never predicted. Physicists are scrambling to explain it. The implications are catastrophic. If entanglement is not truly instantaneous, then quantum computing models are built on a flawed foundation. What is space made of that can slow information traveling at no speed at all? Number 7. The Pioneer Anomaly. In 1972 and 1973, NASA launched two identical spacecraft, Pioneer 10 and Pioneer 11, on trajectories that would take them beyond the outer planets and into interstellar space. Their paths were calculated with exquisite precision using Newton's laws of motion and Einstein's corrections for relativity. We can predict planetary orbits centuries into the future with perfect accuracy. We can calculate gravitational assists off Jupiter's moons down to the meter. These spacecraft should have followed their predicted trajectories flawlessly. They did not. But here is the nightmare. Both Pioneer probes are slowing down, decelerating toward the sun at a rate of exactly 8.74 times 10 to the negative 10th meters per second squared. That number should terrify you, not because it is large, because it is precise. Both spacecraft, launched a year apart, traveling in different directions, billions of miles from each other, are experiencing the exact same deceleration. The value has remained constant for over 50 years. It does not fluctuate. It does not decay. It does not vary with distance from the sun or position in the solar system. John Anderson at NASA's Jet Propulsion Laboratory spent decades trying to explain it. Solar radiation pressure? Too weak and decreases with distance. Gravitational pull from unseen objects would not be constant. Gas leaks from the spacecraft would decrease over time as fuel depletes. Thermal radiation from the plutonium power sources? The math does not match the precision. Every conventional explanation fails because the deceleration is too perfect, too identical, too constant. It is as if an invisible hand is pulling on both spacecraft with flawless consistency across billions of miles and decades of time. Nature does not work with this kind of precision. Random forces do not produce identical effects on separate objects. What is out there in the dark, acting on our spacecraft with such deliberate, unnatural constancy? Number 6. The metallic hydrogen that vanished. Deep inside Jupiter, beneath thousands of miles of crushing atmosphere, hydrogen is squeezed so violently that it stops being a gas. It becomes a metal. Metallic hydrogen, a substance predicted by physicists for over 80 years but never created on Earth. Until January 2017, when Ranga Diaz and Isaac Silveira at Harvard's Lyman Laboratory announced they had done the impossible. They compressed hydrogen between two diamond anvils to 495 gigapascals, 5 million times the pressure of Earth's atmosphere, and transformed it into a shimmering metallic solid. They published their results in Science. They showed photographs. The material was there, glinting under the microscope, a tiny sample of the alien physics that governs the interiors of gas giants. According to theory once created, metallic hydrogen should be metastable. It should remain solid at room temperature and normal pressure, locked into its metallic state like a diamond formed under extreme conditions. It should be stable, permanent, recoverable. But here is the nightmare. The next morning it was gone. The diamond anvil had cracked. The sample had vanished. No trace. No residue. No explanation. In the 9 years since, no laboratory anywhere on Earth has successfully reproduced the experiment. Other scientists have questioned whether the material was ever truly metallic hydrogen at all. But Diaz and Silveira insist they created it. They have the data. They have the photographs. They just do not have the sample anymore. Was it real? Did they briefly open a window into the physics of Jupiter's core only to have it slam shut? Or did they create something so unstable, so fundamentally wrong for our conditions, that it erased itself from existence the moment the pressure dropped? Metallic hydrogen is the ghost material. It appeared for one night in a Harvard lab, and then it disappeared into the dark, leaving behind only questions and a cracked diamond. Number 5. The Tardigrade resurrection. Take a microscopic creature called a tardigrade, also known as a water bear. It looks like a chubby 8-legged gummy bear under a microscope. Seal it inside a container. Expose it to the vacuum of space for 10 days. No air, no pressure. Temperatures plunging to negative 270 degrees Celsius. Cosmic radiation blasting through its cells at levels that would kill a human in seconds. Every textbook on biology says this organism should die instantly. Its cells should rupture in the vacuum. Its DNA should shatter under the radiation. It should freeze solid and never move again. But here is what actually happened in 2007 when the European Space Agency's Foton M3 mission carried tardigrades into orbit. 68% of them survived. Not just survived, they came back from death. After 10 days of exposure to the most hostile environment imaginable, the tardigrades were returned to Earth, rehydrated, and they resumed normal life. They moved. They ate. They reproduced. Their offspring were completely viable. Ingemar Jørgensen at Kristianstad University in Sweden analyzed the results and found something that should not be possible. The tardigrades had been exposed to over 1,000 times the lethal radiation dose for humans. That level of cosmic radiation destroys DNA, shreds cellular machinery, and causes irreversible damage to every known form of complex life, except tardigrades. They enter a state called cryptobiosis, dehydrating their bodies and shutting down their metabolism to near zero. But that does not explain how they survive the radiation. That does not explain how their DNA repairs itself after being bombarded by high-energy particles for 10 days straight. No other organism on Earth can do this. Not bacteria, not viruses, not even the most radiation-resistant extremophiles come close. What is life if it can refuse to die under conditions that obliterate everything else? What are tardigrades using that we do not understand? Number 4. The Hubble tension. There are 2 ways to measure how fast the universe is expanding. Both methods are precise. Both have been refined over decades by the best minds in astrophysics. Both have been verified by independent teams using different instruments. They should give the same answer. They do not. Method 1. Look at nearby stars called Cepheid variables and distant supernova. Measure their brightness and distance. Calculate how fast they are moving away from us. This gives you the Hubble constant, the rate at which space itself is expanding. Adam Rees, a Nobel Prize-winning astrophysicist, has spent years perfecting this measurement using the Hubble Space Telescope. His answer, 73.3 kilometers per second per megaparsec. Method 2. Look at the cosmic microwave background, the afterglow of the Big Bang itself, captured by the Planck satellite. Analyze the tiny temperature fluctuations in that ancient light. Use those patterns to calculate how fast the universe was expanding in its infancy, then project forward to today. This method gives you 67.4 kilometers per second per megaparsec. But here is the nightmare. That is a 9% difference. It sounds small. It is cosmologically catastrophic. A 9% error in the expansion rate means the universe is either billions of years older or younger than we thought. It means our models of dark energy, dark matter, and cosmic evolution are fundamentally wrong. Both measurements are getting more precise. The error bars are shrinking. With better data, the 2 numbers should converge. They should meet in the middle. Instead, the gap is widening. The discrepancy is growing stronger with every new observation. Physicists have started calling this the Hubble tension, but that is a polite term for what is actually happening. The universe's expansion rate refuses to make sense. Either dark energy is changing in ways we cannot detect, or there is new physics operating between the early universe and today that we have never seen. How can the cosmos disagree with itself? Number 3. The time-dilated muons. Right now, cosmic rays from deep space are slamming into Earth's upper atmosphere 10 kilometers above your head. These collisions create particles called muons, unstable cousins of electrons. Muons have a half-life of 2.2 microseconds. That means in 2.2 millionths of a second, half of them decay into other particles and cease to exist. They travel at 99.8% the speed of light. At that velocity, it takes them 33 microseconds to reach the ground. Do the math. In 33 microseconds, a muon should decay 15 times over. Only 1 in 32,768 should survive the journey from the upper atmosphere to sea level. But when we place detectors on the ground, we find that 1 in 10 muons make it. That is 30,000 times more than should exist. Einstein's theory of relativity explains this. Time dilation. At near-light speeds, time slows down for the muon. From the muon's perspective, only a fraction of a microsecond passes during its fall. It experiences less time, so it does not decay. The math works perfectly, but here is the nightmare. When you measure muons in space, the numbers break. The Alpha Magnetic Spectrometer, a MS-02 mounted on the International Space Station and led by Samuel Ting at MIT, has been detecting cosmic ray muons since 2011. The measurements show something impossible. The muons in space are experiencing additional time dilation beyond what Einstein's equations predict. They are surviving longer than relativity allows. Time is stretching more than it should. Space itself is warping time in ways that general relativity does not account for. This is not a small discrepancy. This is time refusing to flow at the rate the universe's most successful theory demands. If time does not behave consistently everywhere, if space can bend time beyond Einstein's predictions, then what is time? Is it a dimension, or is it something more fragile, something that breaks under conditions we are only now beginning to measure? Number 2. The quantum Zeno effect in orbit. In quantum mechanics, there is a phenomenon so strange it sounds like science fiction. If you continuously observe a quantum system, you prevent it from changing. It is called the quantum Zeno effect, named after the ancient Greek philosopher who argued that a watched arrow never moves. On Earth, the effect is real but weak. Observe a radioactive atom constantly, and you can slightly delay its decay. Observe a quantum particle trying to tunnel through a barrier, and you slow its progress. The effect has been measured in laboratories for decades. It is subtle, measurable, predictable, but here is the nightmare. In space, the effect becomes a monster. The Cold Atom Lab aboard the International Space Station, operated by Robert Thomson's team at NASA's Jet Propulsion Laboratory, has been studying ultra-cold rubidium atoms and Bose-Einstein condensates in microgravity since 2018. These are quantum systems in their purest form, isolated from thermal noise and vibrations. When researchers continuously measure these atoms, attempting to observe their quantum state transitions, the Zeno effect becomes 40 times stronger than it is on Earth. 40 times. The quantum states freeze under observation with an intensity that has no theoretical explanation. Continuous measurement should delay state changes by a predictable amount based on the frequency and precision of observation. The math works on Earth. In space, the atoms refuse to change states as if observation itself has become a physical force orders of magnitude more powerful. We can land rovers on Mars and detect gravitational waves from colliding black holes, but we cannot explain why watching a quantum system in space freezes it 40 times more effectively than watching it on the ground. Does space amplify the coupling between consciousness and reality? Or does Earth's gravity and magnetic field somehow suppress quantum effects, and we are only now seeing how quantum mechanics truly behaves in its natural environment? If observation affects reality more strongly in space, does that mean consciousness interacts with the fabric of the universe differently depending on where you are? Number 1. The quantized redshift anomaly. When you measure the light from distant galaxies, you see redshift. The wavelengths of light are stretched because the galaxies are moving away from us as space itself expands. The faster a galaxy recedes, the more its light shifts toward the red end of the spectrum. This should be a smooth, continuous distribution. Galaxies at every possible distance moving at every possible speed, creating a seamless spectrum of redshift values. That is what the Big Bang model predicts. That is what every cosmology textbook says you should observe. But here is the nightmare. In the 1970s, William Tift at the University of Arizona discovered something impossible. Galaxy redshifts are quantized. They do not occur at random values. They cluster at specific intervals, exact multiples of 72 kilometers per second. Then harmonics of that value, 36, 24, 18 kilometers per second, like a digital signal, like discrete steps on a staircase instead of a smooth ramp. Over the past 50 years, multiple independent surveys have confirmed this pattern. The Sloan Digital Sky Survey, the 2-degree Field Galaxy Redshift Survey. The quantization appears in dataset after dataset with statistical significance reaching 6 sigma in some analyses. Mainstream cosmology ignores it. Most physicists dismiss it as observational bias or coincidence, but the pattern refuses to disappear. It persists across decades, across instruments, across survey methods. If space expansion is quantized, if the universe operates on discrete values instead of continuous ones, then reality has a resolution limit. Like pixels on a screen, like frames in a video, like lines of code in a program. There is no known physical mechanism in our cosmological models that would cause this. No force, no field, no interaction that makes space expand in exact increments. The universe is behaving like a digital system, and we have no explanation for why. Are we living inside a simulation with a frame rate? Is reality fundamentally discrete at the largest scales? We are staring into the dark, measuring the cosmos, and finding evidence that the universe might be code. If you enjoyed this video, give it a like, and drop a comment letting us know where you're watching from, and subscribe for more.